Okay, a dice manufacturer claims his novelty dice he produces has the probability of scoring the numbers 1 to 5 are all equal, and the probability of scoring 6, 2 times the probability of scoring any of the other numbers. To test the manufacturer's claim, one of the novelty dice is rolled 350 times, and the scores recorded on the die are shown in the table below. A chi-squared goodness of fit test will be used with a 5% significance level. So A, find the probability of scoring a 6 when rolling the dice. So what's the probability of scoring a 1? We don't know, so we'll call that X. So the probability of scoring a 1 is X. The probability of scoring a 2? Also not known, also X, but it's the same X. So for 1 to 5, there's 5 lots of X. What's the probability of scoring a 6? 2X, it's twice as much. And then the total probability has to add up to 1, because it's certain that we'll get one of the numbers 1 to 6. So this implies that 7x equals 1, which means x equals 1 over 7. So the probability of rolling a 6 is 2 over 7. So B, find the probability of scoring more than 2 6s when the die is rolled 5 times. When we see a probability like this, where we're rolling the same thing, we're doing the same thing again and again, you've got the same probability for every one, and you have a set number of trials. What method should we use to solve this? It's that key part, the set number of trials. Set number of trials. We're doing it 5 times, the same thing. Binomial distribution. This one you have to sort of say, wait, that's a binomial distribution. So if we make a discrete random variable, x, which is binomially distributed with a set number of trials and a probability of success of 2 over 7. So x is our random number, and it will count, x will count how many times we get 6 out of the 5 trials. So it will tell you the probability of getting no 6s, 1 6, 2 6s, 3 6s, 4 6s, or 5 6s. We want to know the probability of scoring more than 2 6s. So the probability that x is greater than 2. Now, for the discrete random variable, we want x greater than 2. That means that we're going to say that x is greater or equal to 3, because those are the same. And on the calculator, we need to include the end values. So we always make it a greater or equal or a less than or equal on the calculator. So we want the probability that x is greater or equal to 3. X is the number of 6s when we roll it 5 times. So menu probability distributions, B. So menu probability distributions, and it's B. You want the binomial CDF, it's cumulative, because you're not taking one value only, it's not equal here. It's an inequality here, it's CDF. If it's an equal sign in here, it's PDF for a particular value. In this, it's a cumulative or collection of values. So the number of trials is 5. Probability of success 2/7. Our lower bound, that's why we move it to 3, is because the lower bound has to be set at 3, not greater than 2. And the upper bound is going to be 5, because this maximum of 5. This gives us a probability of 0.145. So in C, we need to find the expected frequency of each of the number if the manufacturer's claim is true. So we're going to need to take this table of data and add an extra column. Like this. For the expected frequency. We can calculate this because we're rolling it 350 times in this experiment. So we need 350 times 1/7, which is 50. And we need 350 times 2/7, which is 100. We would expect to get 50 of each of these. And 100 sixes. And those are the expected frequencies. So determine the conclusion to the test. So for D, we need to carry out a chi-squared goodness of fit test. For this, we'll need a null hypothesis. And we are looking at the manufacturer's claim is correct. So to determine the conclusion, we're going to need the p-value. So there's our data. So let's add a spreadsheet page. Here we have the frequencies. And here we have the expected frequencies. So type in that table, 32, 57, 47, 58, 54, 102. Type in your table of values, go on to calculator page. We need to do our chi-squared goodness of fit test. The menu, statistics, stat tests, and number 7, the chi-squared goodness of fit test for independence. So observed list is F, expected list is expected, and then we need to calculate the degrees of freedom. So we need the degrees of freedom, which is rows minus 1 times columns minus 1, which is going to be 5 times 1, which is 5. So our degrees of freedom is 5. This gives us a p-value of 0.0984. So to conclude the test, always compare the p-value to the significance level. And we're doing a significance level of 5%. Which one of these two is bigger? The p-value? So the p-value is greater than the significance. significance level. This implies there is, now if the p-value points into the significance level, there is insufficient evidence. To reject the null hypothesis. So with the conclusion, there is either sufficient evidence to reject the null hypothesis or there is insufficient evidence to reject the null hypothesis. If the p-value points into the significance level, there is insufficient evidence to reject. This means the manufacturer's claim is true. Or correct.